The Doctoral Research Award is awarded every year to a promising young researcher working in the area of constraint programming who defended the thesis within the previous 2 years. Recipients before were, I think, Geoffrey, I've seen Stan is somewhere in the audience, Guido is here, Chris, all of them are actually here. They're actually working all in the area of constraint programming. So this is a very nice achievement as well. And the award for 2013 goes to Thias Gans, sitting here from the University in Leuven in Belgium, working on a thesis on declarative pattern mining using constraint programming. And the supervisors Luc Derat and Siegfried Nissen. There's a honorable mention for Justin Yip from Brown University for work on set constraints with Supervisor Pascal. And the selection committee was for the Doctoral Research Award with Gilles Pesson, Mark Wallace and Willem. So thanks very much to the selection committee who had actually to work through a large number of submitted theses. So there was a lot of good work presented. And it was not an easy choice, but yeah, I think Thias is the recipient for this year. I know him a little bit from the FP7 project ICON, where we are working together on inductive logic programming. Thias made his studies in computer science in Leuven in 2006, correct? 2006, yes. 2007, something like that. And then started on the thesis in Leuven as well. He has been the recipient of 2 other very nice awards. So one is the ECAI Award for Doctoral Thesis, which was awarded for 2012. And the other, also quite impressive, is the Belgium award, the Wolsey Award, for an open source system which has an impact on operations research, and that was on item set mining. So he's very busy and very active in the open source community in Belgium and is helping organizing conferences there as well. And he has been working on setting up the Cocoa Mill workshop at ECA last year and at AAAI, and there are other workshops where this kind of work is actually now moving into a larger research community. So I'm very pleased to present the award for the Doctoral Research Award of the ACP to Thias.
Thank you very much.
Nice. And you will probably have to set up your machine.
That's a very nice award. Looks difficult to fake, like money bills. I guess there's no need. Okay. I have to start the recording for the video. Okay. All right. So thank you very much, Helmut. That was by far the longest introduction that I have received so far. I would also like to take this opportunity to thank the people that were member of the committee selecting this thesis. And actually, I would also like to thank all of you, because so the CP community, the lab I'm from is a data mining and machine learning lab, and I've been applying in my thesis constraint programming on data mining problems. And so in fact I've been using and building on technology that has been developed by this community for many years. And when I started 5 years ago, I actually believe that 10 years ago what I've done would not yet have been possible, simply because the solver technology was not yet there and was not yet available. And I think it's pretty exciting also for the things that will be possible in the next 5 years, for example. But okay, let me start. So this is my, that's the cover picture of my thesis, by the way. There's a story behind it, and if you want to hear it, just ask me in private. So my work is situated in the field of data mining and pattern mining more specifically. Now, what is pattern mining? Well, we could summarize it as the field that's concerned with finding regularities in data. And so you can have different types of data in which you want to find different types of regularities. So for example, in text mining, you're given texts and sentences, and you're looking, for example, for recurring sentences or recurring words of groups of words. In graph mining, your input data is graphs. This could be, for example, molecules that are represented as graphs. For example, in drug design, people are looking for certain graphs or certain molecules that react positively to a certain disease and not negatively, and so forth. And another type of data or problem is item set mining, where you're given a collection of purchases. So every row is one purchase. And for example, people have bought books, and you're looking for books that people have bought together, for example, to use in Amazon recommendation or so forth. Now, what people are typically looking for are interesting patterns, but of course there are many definitions of what an interesting pattern is. For example, which pattern appear frequently in the data, or have a certain structure, or contain certain elements, have a high cost or a high profit margin, and so forth. And in fact, each of these ways of expressing what an interesting pattern is can be seen as specifying a constraint on your pattern. And this has led to the field of constraint-based mining. And in constraint-based mining, there have been numerous types of constraints defined, but also numerous systems have been developed, almost one-to-one for every constraint, a new system. And so what we see is that whenever people propose a new constraint, it's accompanied by the new implementation of the whole system, which makes it very hard to combine different constraints. And well, this led us to the question, is a more principled approach possible? And I guess you can guess which approach I've taken in this work. So this contrasts rather sharply with constraint programming. And for us, constraint programming, we use it as a general combinatorial problem-solving method. With this separation of model and search. And so this declarative specification of constraints that you're all familiar with was actually pretty much unheard of in the constraint-based mining community. And so surprisingly, CP had not yet been used in pattern mining. So the problem that we started with, I showed you there are many different types of data, is that of item set mining. It's the most fundamental problem in pattern mining. It's been well studied for over 15 years, and there have been many constraints, but also many applications. And the most standard, simple problem, let's say, is that of frequent item set mining is a problem for which the a priori algorithm has been developed. And so what you're given is a set of purchases, for example, books and people that bought those books, and you're looking for a set of items, so a set of books that appear frequently together in your data. Let's take an example. So the two books on your right, for example, they're bought by the blue and the green guy, and what we say is that the cover is hence this blue and this green guy, and the frequency is the size of the cover, and that's 2. If we express this as a constraint satisfaction problem, then what we can do is we can add a Boolean variable for every book, so for every item, as well as a Boolean variable for every transaction, and then we need to encode the two constraints, so the coverage and the frequency, well, as a constraint. The coverage, to start with, you could say that every transaction is covered if and only if the item set, for example, the two books on the right, is a subset of your row in the matrix. And the frequency can be calculated by summing over these transaction variables, so the Boolean variables corresponding to each row. Now, of course, if you formulate this and give it to a CP solver, not much will happen. So we reformulated it over Boolean variables to get a formulation that actually performs well. You shouldn't worry too much about what it looks like or does, but what's important is that, so this is the type of constraint that we use most, which is a reified linear sum over Boolean variables. And the nice thing is that you can express this, for example, in essence, and you're probably the audience that will be the least surprised by this, to say this because it's familiar for you, but if you show this to data miners, then they basically don't really believe it, because the amount of codes, of lines of code that have been written to do item set mining, the a priori algorithm and improvements on it, is typically way more than 12 lines. So for us, this is the nice part of this declarative side of constraint programming. Now, the good side is that once we discovered how we could express, so these two basic constraints, the coverage and the frequency, we discovered that many of the other constraints that have been formulated in the constraint-based mining literature can actually be formalized in a similar way. So there's a number of them, and you can see that it's a matter of tweaking the sums. There are also more complex constraints that I'm not showing here, but the point is that all of a sudden we could actually formulate a wide range of constraints in one single framework, which also allowed us to combine these constraints. And this, in fact, was unheard of at that time in the constraint-based mining community. So our constraint programming-based approach was actually the most general system, and it still is to date. So these are a number of constraints, and these are different systems, so imperative systems, some of them which were created to be somewhat generic, but none of it tips the genericity of the approach I just showed. Now you might be wondering, what about efficiency? So if we take the most standard task, so this frequent item set mining problem, which has just two types of constraints, what we see is that the specialized systems, they have a rather similar behavior. They form a band here at the bottom, and then our model written in G-code is slower. But what we see is that the behavior is kind of similar. Now, if you look at one of those constraint-based settings where there are more user-defined constraints, then what we see is that the specialized systems, so either they don't support it, like the yellow line, and they would have to post-process all the patterns, which is a lot slower, or one of the systems actually implemented this combination of constraints into the search algorithm, but in fact, using a generic constraint-based approach, was able to be faster. So there is good news, namely that if you add more constraints, even on runtime, there's a benefit for using constraint programming. Okay, now this was a bit the base of our work, and we've extended this work into a number of directions, and I've chosen a few that I hope might interest you. The first is called correlated item set mining. And correlated item set mining is known under many names, but the key idea is that you have your data as before, but this time for each transaction, so for each row, you also have a label. So, for example, positive or negative, as is typical in machine learning. And the goal then is to find the individual item set, so the combination of books of items that best correlates with this class label. For example, this one correlates better with the positives than this one. And when we were studying this problem, what we saw is that they have this correlation function. It could be chi-square or information gain or whatnot. And it's a function on the transactions with a positive label and a negative label. And in the literature, people were using pruning techniques which only use the upper bound of these sum over transactions. And if we applied the standard bounds consistent principles from constraint programming and developed our own global constraint for such functions, which is both the upper and the lower bound, and also this reified formulation I must add, so that the two together, then we get much stronger propagation. And the results were actually rather impressive. So The two systems on your right, they're imperative handwritten algorithms for this one specific task. And the CP column is again using G-code, to which we added this global constraint correlation constraint, but reused our other frequency and coverage constraints. And actually the runtime is lower in, I think, all cases, or almost all cases. So that was very nice. Another thing that we looked at, what I showed you before, is that when we use G-code, it's actually slower than the specialized mining algorithms. It's one of the things we were wondering, and many people were asking us, is like, is there a structural downside to using CP, or is it just a matter of overhead in the solver? And this is what we've studied in this work, cited on the right. And we actually developed a kind of hybrid CP system, so a specialized CP system. And I will show you some of the things that we changed in it. So the first thing is, let's look at the variables and how they're represented in item set mining and constraint programming. So in item set mining, well, you can either represent it dense, so as a bit vector, or sparse, using lists. And in item set mining, well, the a priori algorithm uses a sparse representation, but the really fast ones, they all use a dense bit vector representation, because then they can use bit vector calculations. And if you look at CP, G-code in this case, but I think it's similar for others, then actually it's saved as an array of booleans, and each boolean has its separate upper bound and lower bound. And so what we did in this specialized CP system is we represent an array of booleans as a bit vector of the upper bounds and a bit vector of the lower bounds. And that allows us to write propagators that actually can work on these bit vectors, and that's a lot faster. It's similar to vectorization, something that's also known in machine learning to work well. Another thing we did is that, well, another thing we studied is the data. So typically in data mining there's a lot of data, right? And in item set mining, the algorithms take very good care to keep the data together and to have one data matrix. However, in constraint programming, if we post the constraints, then what happens is that the matrix is decomposed into each of the constraints. And so we have constraints over the rows and constraints over the columns. So that's already duplicates and splits the data twice. And then the constraint solver also keeps indexes on those things. So it kind of like keeps the data 4 times in memory. And this is the biggest problem for scaling up the existing CP solvers. And so what we did is in our hybrid approach is we created, well, we just made one shared matrix over which all of the propagators are then posted, so they share this matrix. Another thing we did was, but this is very specific to us, I don't think it can be generalized. So, because we have this reified formulation, some of the computations need to be done multiple times, exactly the same. And so what we did is we added, it's probably cheating, but still, we added a kind of cache in which we share facts. So if for example, we know that a sum of a certain variable array, so bit vector, is larger than a certain threshold, then we will put this fact in this shared repository, so it will be known that this is larger, and then all of the other constraints, they don't have to recalculate whether this is true or not. And the last thing that I'd like to mention in this respect is if you look at the search tree of an item set mining, the depth first item set mining system, then actually the root node is the empty set, and then the first child is already an item set in itself. And if you compare that to a depth first choice in constraint programming, then the root node is actually, well, a node in which all of the variables are unknown for now, and then you assign one of them and then another and so forth. So what this means is that actually the zero branch, so using a bit vector representation, setting something to 0, is implicit in the standard algorithms. And what this means in this hybrid CP solver that we created was that the zero branch had to be very cheap. So if you set something to 0, none of the propagators should be activated because it will not propagate. And actually we discovered that it did. And this is related to the half reification that Peter has been working on. So actually the changes that we did, the analysis, can in general be done now using the principles of half reification. And we also needed fine-grained control. Okay, so now you're probably wondering how good did it work? Well, really good actually. So we were actually able to push the specialized CP system at the same kind of efficiency as the data mining algorithms. And we're pretty proud of that. And the most important part is the scalability. So this is a data set which is huge, and so we could load it into G-code for the really trivial cases, but other than that, it didn't really finish. And what you see here is also that the specialized CP system was able to achieve similar scalability. Now, we didn't continue on it to add more standard CP constraints, and for example, there's no ordering of which propagator needs to be activated first and so forth. So it is a specialized CP system and it could be extended, but we haven't tried. But for this case, it worked really well. And of course, because it's using standard AC5 and so forth, you could add more constraints to it and run it. Another thing that we've been looking at is pattern set mining. So what if we're not looking for one single pattern at a time? Maybe I should have said this earlier, and I hope that it was clear, but in our formulation, one solution to the CSP is one frequent pattern. And so we typically want to find all patterns, so all solutions, which means generating all solutions. And so in this case, what we've been studying is if you don't want to find just one pattern, but a collection of patterns that have a global property over all of them, can that also be done? And this is called pattern set mining. And so we use CP, especially the modeling part, so as a general framework for expressing these pattern set mining problems in a high-level natural language. But computationally, it's very challenging to do this. And this led us to actually submit some of these examples to the Minising competition a few years ago. So some of you might be familiar with it. And then a last thing that I shortly want to mention is that we also applied this in a bioinformatics domain, meaning that of cis-regularity model detection, where you have a number of sequences. So instead of people buying stuff, you have biological sequences. And on each of the sequences, you can have transcription factors that bind on it. Now this is not a standard frequent item set mining problem because each of those motifs, as they say, each of those regulators can bind on several locations, but it is related to item set mining. And what we did is we started out from our model from item set mining, and then we added these domain-specific constraints that can take this into account, and that allowed us to formulate this problem and solve it in a relatively good way. And this is published in one of those nice bio journals. Okay, now let me take a step back. I don't know how much time you have. Can you give me an estimate?
5 minutes.
Okay, that's doable. So let me take a step back. So for us, the nice part about constraint programming is that this model and search combination, and in this thesis, well, it kind of illustrates the possible benefits of such an approach to pattern mining, but it's only the beginning. And so this leads to the question, can we develop general constraint systems for pattern mining or even for data mining at work, for data mining at large, and what would be the opportunities and limitations? And so together with Guido Tak, we've been making some first step into a more general language and system. It's basically applying Zinc to these types of problems. And there's some interesting challenges there, and some of them are already finding their way into Minising 2.0 and stuff like that. So, in general, there's Other people have been trying other techniques. You have seen the reified linear constraints. You might already be wondering, can't it be done in SAT or in MIP or whatever? So people have been investigated different kind of solving techniques, but also different kinds of pattern mining tasks. For example, on sequences instead of item sets, clustering, sky patterns, which is related to Pareto optimal solutions, and so forth. So then we can ask the question, okay, so what, according to my belief, of course, does CP offer to data mining and machine learning? And one of the things is for sure this declarative approach, which was previously not really popular, or at least not really believed in. Also the flexibility that you can develop propagators independently of each other, and then from a user perspective that you can actually combine these constraints. This was uncommon in pattern mining. And so the way that I've been using it also is for rapid prototyping and in an iterative process. So the biologist tells you they're looking for that, you write it, and then you tell you, oh no, I'm looking for that, and then you just change the constraints, and that was nice. So, of course, you can ask the other question, what does data mining and machine learning offer to constraint programming? And for sure, I would say that data mining offers new applications, but also very challenging benchmarks. I've looked at amazing results. Apparently, it's not the most challenging problem in the set, but it is one of the very challenging ones. But also, as I said before, there's been a lot of work in data mining on writing very efficient algorithms, and surely there are some things that can be mapped back into constraint programming. And you beat me with the half reification, but there might be other things. There's also new data and pattern types. So I've talked about item sets, but you also have sequences, decision trees, clusters, graphs. I know this nice work about CP graph. I think Evie is here. And there's been a talk yesterday about encoding neural networks into CP. So there's definitely more there. And of course, using machine learning to improve the modeling and solving. This is, I think, a reasonably hot topic in CP already. Helmut mentioned it, that I've been involved in a number of workshops together with some of you. And I would like to just make some advertisement for a special issue on combining constraint solving with mining and learning. So if you're working on any combination, then please consider submitting. Just search for COCOMILE, this abbreviation, and you should find it. Okay, and then before I open the floor for questions, I just want to point to this website that we have, which contains all of the data and all of the models in G-code that we've been developing. Also this specialized system, it's all open source, it's all available, and I invite you to have a look. We also refer to other papers than our own and stuff like that. So thank you very much for listening. Me too.
A question from my side. How reusable are the changes that you made to make a specialized version of the solver? So can one apply that to other problems? And is it just is it something that you could import into the general G-code engine? That makes sense, or is it specific to that problem?
I think some of it can be ported back. So this idea of having a bit vector representation of the Boolean. So if you have an array of Booleans to represent it as 2 bit vectors, and you have propagators on that, I think you could add a new data type. I'm not planning to, but I mean, you can add new data types, and that could make sense. But I think the most promising is the way of handling the data. So in CP, in the typical problems, you don't have that much data, so it's okay that you just distribute the data into the constraints and let the constraints simplify it and handle it. But if you work with really big tables like we do, you actually don't want to split the data up into the separate constraints. And I know that some of the solvers already allow sharing individual vectors, and it might be interesting to also allow sharing entire matrices and to then have indexes on them or something. So I think for problems that have a lot of data, that's the lowest hanging fruit.
I think people are really hungry. Okay, thanks very much.
Thank you very much.